But it's not like it's a different function. It's just somewhere in between. But my goals for like
that's what I had to do. Yeah, we have the data. Yeah.
not good ability for yes.
Are you posting the slides soon?
Yeah, I'll definitely post them. Like Tuesday is going to be the last content lecture, so I'll probably have to post the last two after the Tuesday lecture.
I really like some of those maps, and I want to see the links, especially the ones where they show population.
Yeah, if I think about it, I can do it later today.
Just having.
So a lot of the visualization you do seems to look like they're from news articles.
Yeah.
How about dashboards or?
Yeah, so there's a little bit of a bias in my selection for telling stuff about in class here, right? Because those news articles there is a story that I can tell behind them, and they're usually like engineered so that they're pretty sophisticated and well designed, and I think there's like tons of other areas like dashboards, but like how people don't usually post those, right? They use this internally, and so it's difficult to kind of like discuss this in the class setting. But I hope that most of the lessons apply across the application domains.
How come Excel is like so slow to implement some visualizations? Certain charts. Excel.
I don't know. I think, well, they're doing stuff now, right? They have now a Maps plugin. I think Microsoft is more putting energy towards Power BI rather than Excel. So, yeah, but it's definitely been a boon for Tableau. They made a lot of money.
Could Power BI end up ending Tableau?
What's that?
Could Power BI end up outcompeting Tableau?
Well, I don't think so. Tableau was just sold to Salesforce for, I don't know, a couple of $1 billion.
I didn't know they got sold to Salesforce.
Yeah. And so they're doing pretty well. They have like a really big biz research lab. They have like 10 faculty or 15 faculty level visualization researchers now that just research no product development. Okay, so let's get started. Today we'll be talking about filtering and aggregation. So like this is going to be essentially like a lecture complementary to stuff that we did already. So when we talked about interaction, now we'll look a little bit more about what filtering means. But most of this lecture will actually be about aggregation, and we won't be looking so much at like how to aggregate a table, because we talked about this, but we'll be looking at things like how to actually construct the Voronoi diagram. How do I actually, like, what's the intuition behind clustering algorithm? What's the intuition behind dimensionality reduction and this kind of stuff? This is going to be like teasers, right? So if you want to learn more about any of those algorithms, there are dedicated classes like machine learning or data mining and so on. This is just like, in the context of visualization, what is useful to understand about those algorithms and about these approaches, and so that you can kind of like A, visualize using those, and B, like actually apply them. Okay, so this is kind of like from Tamara book. If we filter, we can either filter items or attributes, and if we aggregate, we can either summarize items or attributes. So what does this mean? Like basically, like recall we talked about items are the independent variables. This would be like things like people. So for example, if we wanted to filter out like all the students with a GP or with like a grade of an A, we would do an item filter. But if you wanted to filter out from the student list all of like homeworks 5 and 6 to only look at homework 1 to 4, then we would have like an attribute filter. And similarly for aggregation. So I could, for example, aggregate either by, let's say, sections, so that I can see what's the average grade for an undergraduate versus for a graduate in this class, or I could aggregate by homework, so that I get the average homework grade, the average project grade, and so on. So when we talk about filtering, it's really about eliminating elements. And so what are potential ways to filter data? It's kind of like super generic. It can be any function that partitions a data set into 2 sets. You can have things like bigger or smaller than x, and x can be anything. A fold change between different like dimensions, for example, or some kind of like statistical measure of whether something is noisy or insignificant. So this can be completely arbitrary. And recall when we talked about interaction, we talked about dynamic querying. And so dynamic querying was about this coupling between encoding and interaction, so that we can immediately see the results of an action. So that, remember, this was like the example, the historical example we looked at, and that we also did the redesign for was the home finder. And then one thing that I like to think about, like are distinct but also very related, is queries versus filters. And so it kind of like you achieve the same thing, right? But with a query, you start out with 0 and then add in elements. And with a filter, you start out with everything and then remove elements. And so which of those do you prefer? Like mostly depends on the dataset size. Can anybody give me an example of where you use a query versus a filter? What's like a query approach that you probably use every day?
Searching a PDF or text document or just web page.
Yes.
I don't want to see everything. I just want to see.
Exactly. So searching, like searching or querying in a PDF, or even like using a search engine like Google. Your approach for using something like Google or like finding information on the web isn't to visualize everything and then narrowing it down. It is really to like write a specific query that gives you a result, and then you export that. And filters are like if you have like a manageable set of items that you all want to see, but then you can dynamically, based on the properties of these items, you can define those filters. And so this is like an historical example for filtering from '94. This is this film finder. So we have like a score of popularity and the time on this in this scatter plot here. And then if you like, they have these sliders here, like the year of production, and then some other sliders. And as you like restrict those filters, you reduce the number of items. And then once you have space, you can actually also show the labels. We did talk a little bit about these scented widgets, and these scented widgets are just like a way of making a little, like one problem with filtering is that sometimes, and also with querying, like you never know ahead of time how big your result set is going to be, right? If you put in a query, like a SQL query into a database, how do you know how long it's going to take, how big your result set is going to be? And this is kind of the idea behind scented widgets, like give people a little bit of an idea of what is behind the data. And so here, like I have a slider, and you could think of this as a filter. I include everything from here to here. By having this histogram on top of it, I give people an idea that, like here, if I slide over here, I probably include the majority of the data set because there's only like few taller bars here on the right. So here's an example, and I did show this before this tool, but I'm going to show this again in the context here of this semantic filtering. This is about like athletes that won Olympic medals, and so you see here a ranked list. Michael Phelps at age 19 won, how many is it? Like 8 medals? Yep. And then he won 8 gold medals at age 23 in the 2008 Olympics. And so here are these scented widgets, right? So they, like, I can kind of like change the filter here, and it will update. You see that everything here is updating, and then I have kind of like there's no 2 medal winners anymore in this data set. And so now I know that like there's not a lot of there's a lot of people in my next bin. So if I were to reduce this, then I kind of like can't expect that my data set is going to be significantly smaller. So this is just like an example of a scented widget in a live system. And similarly to the scented widgets, and kind of like this is almost not a perfectly defined line, are these interactive legends, right? So when you have a legend to, in this case, visualize the size of the bubbles, you could also just like very easily integrate filters to, for example, only include bubbles that are bigger or smaller than a certain amount. So this is kind of like useful for filtering, but as I said, if you really want to talk about larger data sets, you really like want to think about dynamic queries. And so I also did show this tool before, but I just want to show the query here again. So this is like a graph exploration tool, and we have like 40,000 nodes in the backend and like many more edges. And of course, it wouldn't make sense to visualize all of this at the same time because this would just be like a messy hairball. So if I put in somebody like Ben Schneiderman, like now I've run a query, I've like retrieved this person, and now I can simply like add this node, and then now I'm running kind of like interactive queries by essentially just expanding like what are his neighbors and what are this node's neighbors and so on. And so here, like this is a way of like dynamically querying a data set like through interaction by retrieving only the stuff that you really care about. One really cool thing is sketch-based queries. So the idea here is like sometimes we're trying to find a particular pattern, right? Something like, for example, we might try to find like a downturn in the stock market. Or if you use LaTeX at all, you sometimes might have to use some mathematical symbols, and then you might not know exactly the command for it, but you're perfectly able to draw that command. And so this here is an example of, I can actually draw this here, and this is a pie, right? And then, well, it wasn't very pretty, but it still did like correctly identify that uppercase pi might have been what I was trying to sketch. So now, like basically, this was a query interface where I sketched some like a pattern, and some algorithm was able to detect what is it that they actually meant, and now I could use the syntax here to actually like use that symbol. And so this isn't really like for data visualization, but this is a good example. But you can do this for time series, for example. So here, this is a tool that was published at CHI 2 years ago, 2018. And you can simply, like, it allows you to draw a certain pattern, and then it will scan the whole time series and identify that pattern. And so they have here some examples. Like, they did a study of, like, they asked people to sketch these kinds of queries, and they sketched them. And so based on that information of what people actually sketched, they optimized their algorithm. I'm going to play this video because I think this actually also won an award at Chi, and I think this was a really great paper. Now you can sketch a pattern, and it will show you matches and rank the matches. And you can kind of smooth the function below it or behind it. And it even gives you some mathematical definitions if you want to have like a refined query. You can like set periodicity. So you can kind of like make this a little, like, because like one problem with the sketches is they're not in the data dimension necessarily, and so you can define what is the scale that you care about. Okay, so you get the idea. Okay, so now I want to move on to talk a little bit about aggregation. Because like we talked a lot about filtering and so on already when we talked about interaction, and aggregation is a little bit more specific here. So aggregation is really about representing a group of elements by a typically smaller number of derived elements. And we talked about aggregation in like the context of tabular data. We talked about histograms, kernel density estimates, box plots, violin plots, and so on. So I'm not going to repeat all of this. But one thing that we didn't talk about yet is spatial aggregation, right? So like we talked about maps, and in cartography, like we also want to like aggregate data, but it's kind of like we have this modifiable areal unit problem. The changing the boundaries of a region changes like the results quite drastically. And so for example, if we wanted to do a choropleth map, as we talked about last time, showing how many points are in here, it depends a lot about how I subdivide the space. And so what is the like analysis, or where is this problem, where does this appear in our daily lives? When you read newspapers, over the last year, there was a lot of discussion about that.
Gerrymandering?
Exactly, gerrymandering. So how do we actually pick a representative for a particular like area that also is kind of fair to the population? So gerrymandering is this problem of essentially like how do we aggregate space fairly? And so here's like an example. This is an actual map of a congressional district in Pennsylvania here. And of course, this was designed with a particular goal in mind to give one party an advantage. And so this was when like Democrats won 51% of the vote, but only 5 out of 18 House seats when the map was gerrymandered like this. So here's a simple analogy in like that is easy to understand in like in a rectangle. And so if we had 50 people. If we like created those bins here, basically where we have all the red and the blue people separated into their completely discrete elements, then we have like a perfect representation here. if we create here a compact representation where we always slice it such that like all the proportions are exactly equal, we suddenly get like we have the 60-40% ratio. This here is like a good representation, but here we have a completely unfair representation, right? Because the people in that are red don't get any don't get any votes. But then you can also create these like even if you have a majority for voting for one particular party here, you can create these maps by simply drawing these non-compact shapes, where you draw it such that you cluster all of the people that that kind of are likely to vote for one party into one district, and then you make sure that the rest of the districts are just barely on your side. And so what you see here is that you have like this one here is extremely blue, and this one here is extremely blue, but all the other ones are designed just so that red has like a slight advantage, right? By doing that, you actually get, even if you have by population, you have a 60% blue and a 40% red vote, you get 2 blue districts, 3 red districts. And that's how gerrymandering works. And Pennsylvania was a particular interesting case because it actually went to the, it went to the state Supreme Court, and it also went to the United States Supreme Court. The United States Supreme Court didn't make a decision about this, but the state Supreme Court did make a decision that, like, this was, well, this is like the map before that judgment, and you could see that, like, basically here, Trump won 12 districts and Clinton won 6 districts. This was a proposed nonpartisan map where Trump would have won 11 districts and Clinton would have won 7 districts, but you could even create a more extreme gerrymandered map if you just use the right methods, where Trump would have won 15 districts and Clinton would have won only 3 districts in the 2016 elections. And so it turned out that the court had forced the state of Pennsylvania to update the map, and so we now see 2016 and 2018 congressional elections, House elections, and we see that Republicans had 54% of the votes in 2016 and won 13 out of 18 seats in Pennsylvania. And then with the revised map in 2018, Republicans had a declined share of 45, now only 45% of the votes, but they had an even more significant reduction in the number of seats. And so now it's 9 to 9 seats, so Democrats still have less seats than you would guess just from looking at the popular vote, but this is because Democrats naturally cluster in urban areas, right? But this is clearly a more fair map. And so you would think that this is like, Utah doesn't do that, but of course Utah does. And so this is what the Utah congressional map looks like. And so the interesting thing is this was the map until 2002. So essentially you had like two big districts for rural Utah, and then 1 district for Salt Lake City metro area, right? After that, Salt Lake City was sliced up into all the 3 congressional districts here. So you see that after 1 district was added, it was like designed such that like the votes in Salt Lake City would be part of, like, mixed in with all these different congressional districts. And so this is the current congressional map of Utah, and I'm sure this is absolutely intentional to have Salt Lake City sliced up like this. Here is like the current congressional map with the 2016 congressional elections. You can see that like 2016 outcome, unlike 2018, Republicans won every single seat. And if you had like a hypothetical nonpartisan map, you would have 1 Democratic representative in Utah. So maybe like talking a little bit about this, like clearly drawing maps like this, like that are fair and compact and make sense, is a fundamental problem. But what are kind of like some of the approaches that you could take to make this fair?
We're trying to draw a map that just represents the popular vote. Why not just use the popular vote?
Yeah. Yes, you're perfectly right. But I guess the Like this is just like something, yeah. Like if you the idea behind all of this is that if you lift somebody, you have like one person that represents you particularly in government, right? And that you have like one congressman that is responsible for you. But essentially, as long as you like want to stick with that idea, there's no way of ever getting like a completely fair and unbiased map. So yeah, that's kind of like there isn't a solution to this problem. There are ways that you can quantify like what kinds of biddings are somewhat fair and which ones are absolutely unfair, but there isn't a perfect solution. Any other thoughts on this? Yeah.
You sort of go by how many people cluster around a particular point. So if you want districts with 100 people in them, like you figure out like clusters of 100 people.
Yeah. Yeah, so that would be like a more fair representation that you look at population density, but what you kind of like, you say spatial clusters, right? So you're using like a compactness feature. So that's basically, I think, what people nowadays consider as fair maps. So one way, yeah.
Isn't that what the first map's trying to do? It's trying to like get the number of people in each district. So that's why
Yeah, so they're like, I think those two are actually like these are very different approaches of gerrymandering, right? Like the Utah approach versus this approach are kind of different. In the Utah approach, it's like the designer of that map knew that if they were to give all of Salt Lake City one representative, then that would likely be a Democrat, right? And so they decided to slice it up. And here it's the other way around. So they kind of like spread out this district. So this isn't, oops, I'm going in the wrong direction. So this isn't like you see like the Salt Lake County, this isn't like a spatial representation. You can have a neighbor on your street who is in a different congressional district, right? So the idea of like what many people think of as a fair map is that you actually have meaningful spatial areas as representing something. Like here, I think you can have, like, I don't know exactly the cases, but like, yeah, it's hard to see on this map or exactly what it is, but it can be that you slice one neighborhood into two different districts, right? And that's not the idea. Yeah?
Could you, like, potentially make things more fair if you introduce, like, some type of randomness?
What do you mean?
Just, like, randomly drawing these districts, like...
Well, I think you do want them to be, like, if you want those districts, you kind of like, it makes sense to make them compact, right? Because usually, the idea behind this direct representation is that if you live, let's say in San Juan County, you might have like certain, like your constituents there might have certain goals, right? They might be like interested more in water rights than Salt Lake City population would be. So you would have an agent for your like problems. And if you just completely randomized everybody, or the space here, then you could just go to like a proportional representation instead of like a geospatial representation. But one way to slice up things fairly are Voronoi diagrams, right? Or not fairly. This is a different problem, right? This isn't the same problem as gerrymandering, but what a Voronoi diagram is given a set of location for which area is a particular location and the closest. So think of this as like hospitals or airports. What is the closest airport from any given position? That is kind of like what is encapsulated in the Voronoi diagram. So if you are, let's say, if you are in the medical emergency around here, you just look at this Voronoi diagram and know that this is your closest hospital. If you're in a medical emergency here, this would be a closest hospital. Of course, not taking into account anything like traffic or anything like that. We talked about these Voronoi diagrams. Here's this map that I already showed, like the Voronoi world, the Voronoi diagram of the airports. So like it's pretty obvious that we have like pretty dense cells over land, and then we have these bigger cells over the sea. And we also talked about how we can use these Voronoi diagrams to improve interaction. So remember this example down here that makes it super easy to hover hover over like a specific area, and it would automatically select the segment of the line based on like the closest segment to my cursor, and that kind of like makes it much easier to pick and interact with any of those smallish features that would otherwise be tricky to do. But like we talked about this, what we haven't talked about is how to actually create such a Voronoi diagram. What's the idea behind it? And so the way to create it is first you need to create a Delaunay triangulation, and a Delaunay triangulation is simply just like, well, what is a triangulation? A triangulation is you take a set of points in space and you connect them such that you get triangles. Like here, like you have one triangle connecting these 3 points, right? And a Delaunay triangulation is a special type of triangulation that has the property that any like triangle, if you like draw a circle through those 3 edges, similar to what I'm showing here with my highlight, then no other vertex is within that triangle. And so if you then take this Delaunay triangulation and then simply draw perpendicular lines to all of the edges, you get a Voronoi diagram. And so, like, how does this work? How do you actually create such a Delaunay triangulation? Well, there's like a simple approach. Like, it's a little bit more tricky numerically because there's some things that you have to do to test. But to construct a Delaunay triangulation, what you do is you first create any triangulation, and then you run the test whether each triangle is Delaunay or not. And so if we ran this test for this triangle here, we would see that this is not a Delaunay triangle because the circle that I define by the 3 vertices here includes another vertex. So this violates the Delaunay condition. But there's a nice property that if you find something like this, you can simply flip this edge here to like connect those 2 lines here, and what you get, those resulting 2 triangles are a Delaunay triangulation. And so you simply iterate over all of these all of the triangles, test for whether they are like whether this point is within the circle, which is kind of like there's methods to do this efficiently. And then if it's not, you flip. If it is, you just move on. And so that's kind of like the algorithm behind creating a Voronoi diagram. Okay, so I want to do a design critique now. We've talked a little bit about the GapMinder tool, but here I want you to like actually play with this tool. But because this design critique is really mostly about the interaction, so like go to this website. I'll hand out the sheets in the meantime. And please feel free to discuss in the group again. Like the one where you actually draw a line between points.
Okay, so let's talk about this. Like, what's the data that we can show in this visualization?
Income life expectancy.
Income and life expectancy, but is that all?
They have to drop down.
Yes, so like, well, we have drop downs, right? So like we have a lot of different data sets that we can select here. But what's like the larger category?
So there's two dropdowns, but they both have the same set of like demographic data for given countries over time.
Yeah, so we have basically data about countries that includes health, education, energy, environment, and so anything that essentially like you might care about if you want to do like if you want to make policy in some way, right? And so how is this data encoded?
You've got positions for the two attributes that you decide on, color coded by continent, and the radius is also assigned.
Exactly. So you have 4 different dimensions that you can do here. You can pick numerical dimensions on the x and the y axis. You can pick the size of the bubble, and you can pick the color of the bubble. And all of those is actually you can freely pick them interactively here. And so this is kind of what we call these view specification. If you think back to the Jeff Hare and Ben Schneiderman paper about interaction for visualization, they talk about view and data specification. And this is kind of the type of interaction that you have when you switch here between things like child mortality and income. Okay, so one other thing that we didn't talk about yet is the time slider. Any thoughts on this? So what does it do? Anybody?
Chooses the year.
Chooses the year, yeah. So the problem that it's trying to solve here is what?
Oh, I was going to say it's not quite this good in here. It actually seems like it's quarters.
Okay.
It's actually 4 to 6 months per year.
Yeah. I don't know. I have a hard time picking them, but I guess you can. There's this thing here which I don't actually know what this does. It doesn't say. Anyways.
You think it might be speed.
Speed. If I run the animation. Okay. So yeah. So this is another feature here that I can click play. Yeah. Now it's very fast. Now it's very slow. Yeah. Great. So why animation?
To see change over time, growth.
Yeah, exactly. So with this animation, we can kind of see ourselves to change over time. So we talked about different approaches, like small multiples, right? They also have this other nice thing here that you can pick one particular country, and then for that particular country, you should be able to see the trail. I don't know if that's
The trail only goes forward, it doesn't go.
Yeah, here we go. Okay, let's jump here. Now we see Ethiopia's trail over time. So that's kind of like one way of seeing the path of Ethiopia. And we've seen this before, right? And clearly, if you did this for all 180 countries, that wouldn't be all that useful. And so, what do you think? Are these the interactive features you valuable?
Yeah, I especially like being able to see a general change as we go through time, while also following an individual country. Because if you get to about 1918, you can actually see a huge drop in life expectancy due to World War I.
Yeah. Oh yeah.
Or the Spanish flu.
Yeah. Do you see the same drop? Not quite as
Only
pronounced.
with the European countries for World War II.
Yeah.
Kind of wrong.
Yeah. Yeah, so that's really cool. And you have thoughts on interaction? Is it one interaction that is kind of very pronounced here is that as soon as I select the bubble, everything else fades, right? What do you think about that?
I guess it's useful if you just want to focus on that one characteristic and then see how it changes over time. Because if you have all the colors available, and then you see the changing around search and it can get kind of muddled.
Yeah. Yeah, they also have this hover interaction here and this crosshair. And this crosshair kind of gives you specific detailed values, right? And this halo and hover shows that your mouse is resting on that. But I would be curious to see how this halo would work, instead of graying everything out. one gripe I have with the interaction here is that it's super flickery. So I think especially if I interact here, like things are like jumping around a lot. It's not as like, yeah, you can see what I mean now, right? So like what I would do here is to kind of like delay this a little bit, that you have to rest your mouse for a couple of milliseconds before you actually change something. But overall, what do you think? Like, is this visualization effective? And like, who do you think would want to use this? And how is this different from, let's say, something that the New York Times would publish?
I mean, something just interacting with it is it gives you a lot of control over what you see. And so giving this to someone who may not have very much experience with visualization would be really overwhelming. And so it's probably more for a professional audience.
Yeah, exactly. And like, what is also different from like most other visualizations we looked at, like especially from newspapers?
They're usually trying to tell a story, and so they'll give more context. This is not so much trying to tell you something, it's just to show you the data so you can make it.
Exactly. This is like a completely neutral visualization, right? It just collects the data. It doesn't even like curate it. Well, it does a little bit of curation by saying, hey, here are some interesting variables at the top level, and for everything else you have to drill down a little bit further. But it has even like features that I would consider are often tricky, like are often tricky, like a log scale, right? So that's something that you don't usually see in a newspaper visualization, but for some types of data, this is like absolutely necessary. And so yeah, like I would agree with that. This is like likely designed for somebody who like maybe like college students that really want to like, or are asked to really explore this data, but maybe even policymakers. And so remember the very first lecture I showed this video of Hans Rosling from his TED Talk, and he used like an older version of this tool to kind of like make his point. So he was telling his stories in his presentations, but the tool itself is like unbiased. One other thing that you might have noticed is here the URL kind of gets pretty complicated. Like what's going on here?
It's a database access, right?
It could be. I think more generically, you could say this is like just basically the state, right? It essentially tracks the state. So if I were to configure this and send this to somebody else, I could share it like this, right? I could simply send it to my colleague and say, hey, here's what I found. And it will contain all of the information. So that's kind of like a nice feature of visualizations, especially if you want to work with somebody else and share what you do. Yeah?
I thought something that was kind of funny is that when you hover over a country, it highlights the continent, like we don't know where like China is. You know, given that it's for experts or whatnot. Like, I don't know. I thought it was a feature.
You're right, but like some countries, you like depending especially where you live and grew up, you might not actually know, right? So, but I agree. Any other comments? Okay, great. So let's move on. Now I want to talk a little bit about clustering, because like we've talked about clustering applications when we talked about Tableau data, and when we talked about networks. Like, what are kinds of the dimensions along which you can think about clustering? So, like, what does clustering do? Like, clustering is about classification of items into similar bins. And clustering is like an unsupervised learning method, right? So, like, unlike supervised learning methods, we don't have usually a labeled data, or we don't have a labeled data set that we want to compare and then like do some prediction in the future. We have like data, and we want to simply generate groups of similar items. And that doesn't mean that they are like they have named clusters of bins or anything like that. And so what you do is you use some kind of similarity measure to say whether two items are similar. And of course you can come up with anything, but if you have like a numerical data set, then something like the Euclidean distance or person correlation or Chebyshev distance or anything like that would be like a reasonable measure of similarity. But as in any algorithm, like picking like there's a lot of parameters that you have to pick through a cluster, like including selecting a cluster, and picking the distance measure is an important one here. And then I like to distinguish between 4 different types of clustering algorithms, and they have all different implications for visualization. So partitional algorithms divide the data set into like a set of discrete clusters, or bins. And the number of bins or clusters are like either typically manually set in an approach like k-means clustering, or automatically determined, like in affinity propagation or in db-scan or anything like that. Hierarchical algorithms, in contrast, they don't produce discrete bins, but they produce like what's called like a similarity tree, like that you can visualize as a dendrogram. So what are the elements that are closest to each other, and then you can cut through that similarity tree to create dynamically create discrete clusters. You might have heard of biclustering. So these are clustering algorithms that cluster, like if you have a tablet data set, cluster both the items and the dimensions, or the dimensions and the records simultaneously to find like a global optimal grouping. And then finally there is fuzzy clustering. So fuzzy clustering doesn't create discrete bins or a similarity tree, but essentially gives you a probability that an item belongs to a particular cluster. And fuzzy clustering is often, like, not everything is binary and easily distinguishable, right? So, not everything is in a clear category. So fuzzy clustering often is actually like a great way of modeling something that isn't quite as clear-cut in the real world. But of course, like if you think about this, there's a lot of implications for visualizations, right? Fuzzy clustering, visualizing fuzzy clustering, I suddenly can't use color coding anymore for items on a scatter plot because they might have multiple colors. If I have hierarchical algorithms, I don't have a predefined number of clusters, so I need a way of kind of like what are the number of clusters that I want to visualize. And partitional algorithms are kind of like the simplest way what you usually think about. And so in this, what can we use clustering for? Like we can basically use it for ordering, not exactly for seriation, but at least to bring all of the items that are similar into the same neighborhood. So we talked about this in the context of heat maps. For brushing, if we have any kind of geometric techniques, so we can kind of like brush elements that are in a cluster, and of course for aggregation, because like the idea of clustering is that the items in a cluster are homogeneous. So I can maybe, like instead of representing every single item in the cluster, I can represent all of the items in the cluster in a more abstract way. So if I do that, any kind of statistical measures, like the mean of a cluster is likely more meaningful than the mean of the overall data set. So here's an example of where ordering plays a role. I did show this when we talked about tabular data. This data set is kind of like you can actually see patterns once you've clustered it. So like we clearly see that there's 5 clusters here, like 1, 2, 3, 4, 5. And we can also probably guess at some clusters in the y direction. And of course, clustering, like it has to work for the particular technique. For parallel coordinates, it doesn't work. For a heat map, it does work well. Here's an example of like how we can actually compare clustering. Like these are 2 different clustering results, and we can actually see like where do the different elements occur in the different clustering results. And so this is like a focus and context technique in a heat map, and I've selected this cluster, and I can see that this cluster here in this other data set is kind of like split between this cluster, and then there's some other outliers in this other cluster. So this is similar to like the parallel sets technique that we talked about for visualizing categorical data. So if we want to see like cluster stability, we could do that. Here is an extreme example for aggregation. So here, like we have like this is like one subset of the 5 dimensions of a data set that was clustered, and we have something like 10 clusters. And the idea here is that each of these clusters is like fairly like homogeneous. You see that you have this like down, up, stable trend here, and then here you have this, all of these elements are low trend here. And so by like separating those clusters into these separate visualizations, we can do very compact representations, like here, green, green, red, 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 to represent the underlying data, and we are probably not going to miss all that much of the features. So, like, what are some clustering algorithms, and what's the intuition behind them? So, k-means is like probably like the most well-known clustering algorithm, and the goal of k-means is to minimize the aggregate intra-cluster distance, so the inertia of a data set. And so what you do is you calculate the total square distance from the point to the center of its cluster, from each point to the center of its cluster, and you try to minimize this. And for Euclidean distance, this is also the same as the variance. And so, like, you can think of the intra-cluster distance also as a measure of how internally coherent clusters are. But, like, how do I actually construct k-means? So, like, one way of constructing like the k-means clustering is with Lloyd's algorithm. So you have like some input set of records, and you have an input k. And k is given. This is a parameter that you as a human have to set. So it could be something like 3 or 4, and then you get 3 or 4 clusters. What you then do is you pick k starting points as centroids, or just 3 starting points in your space. And then you run an algorithm. While not converged, for each point you find the closest centroid. So like if I had 3 centroids, I would evaluate the distance from each point to each of the 3 centroids, and then I pick the centroid that's closest as my cluster. Then I assign that point like to that cluster, and then after I've done this, I compute a new centroid. So like after I've assigned those points, I like use a weighting by calculating the average of all assigned points. I calculate a new centroid. So this is moving over the centroid, and then I do another loop. And so you can see that this iteratively will kind of like improve this intercluster distance. You repeat this until you converge, and there's different sets of criteria that you could use for convergence to terminate that loop. For example, you could say if no point has changed the cluster between 2 iterations, you could stop it. If the distance between the old and the new centroid are below a certain threshold, or if you like just want to make sure runtime is like limited, you can also say like we have a max number of iterations. So like here's a little bit of like a graphical representation of what I just said about Lloyd's algorithm. So here the squares are data points and the circles are centroids. And so I've initialized these centroids. And now in the first step, I would calculate for each of those squares, what is the centroid that's closest to it? And then assign the clusters. And so here I've highlighted which are the points. And then in the next, like, this is, like you see that, for example, this point on here is closest to this one. This point on here is closest to this one, and this one is the only point in that cluster. Now I calculate new centroids based on the points that are in that cluster. And so what's going to happen with the red one?
Good, jump over to square.
Yes, it's going to be exactly the square, right? So it's going to move exactly on top of the square. The green one is going to shift down a little bit. The blue one is going to shift up a little bit. And then I have a new cluster assignment. So I keep doing this until I reach some termination criteria. Okay, so here's like a really nice visualization of how I can do this. So I'll choose for now, I'll do a Gaussian mixture, and I have these 3 points, and I'll pick my centroids initially. And then if I run the clustering algorithm, this is going to be fairly easy, right? So like now it's been assigned correctly, and then it moves them into the centroid, no point has changed. And now I can kind of like keep doing, but this isn't going to be all that interesting. So let's say if I'll choose, let's see, what, if I pick my cluster, my points like this, what's going to happen?
The red's going to hop over the middle, green's going to go up here, and blue's going to be stuck.
Yeah, so blue is an interesting case, right? So like after we update the centroids, blue might actually get something to do. So I can now reassign the points, and then update the centroids. And so it looks like we will actually find a good solution here, even though my initialization was really bad. Now let's do something like even trickier. Okay, and now we'll see what happens. Oh, it actually figured it out, even in this case.
Opens to be at 4 points.
Yes, that's a good point. Let's try it. I'll pick Gaussian mixture again. What happens if I have 4 points? So this was kind of like a good solution, but this isn't guaranteed, right? If I do something like this here, what do you think is going to happen here? Like, what would be, you as a human, what would be the clusters here?
Outside bring to the eyes. And then
Exactly. And so, will k-means be able to do that?
No.
No. You, like, even if I try to like initialize it really well for k-means, it will not be able to actually detect this pattern. So it really, like, this pattern isn't something that you can easily do with k-means. And so one point that I also wanted to make is about initialization. Like I've picked these points like either like adversarially or kind of like nicely, but of course like picking my initial points is going to be important here. Like k-means will never find a global optimal solution, or like is not guaranteed to find a global optimal solution. It kind of finds a locally optimal solution, and so a lot of it depends on my initial selection of centroids. And so one strategy of picking centroids is farthest point strategy. So you, like what you actually do is, let me show that, by, like I add a centroid, it picks a random point, and then it picks the point that's farthest away from it for my next centroid. So blue is as far away as possible as from red, and then the next point it picks is again as far away from both of those points. And so this is like a good initialization now, and that is a heuristic that you can use to initialize a data set. Okay, so another question that you have to ask yourself is, how do I choose my K? Like what would be strategies to choose my number of clusters?
Try all of them.
Yes, it's actually not an uncommon strategy. So it turns out that k-means is very, very efficient. And so you can simply try all of them and then evaluate which of them is actually the best one. You could do that visually, but you can also do something like silhouette plots or calculating on intercluster distance. And so I have an example for that in a second. Yeah, try all of them is really what you do. And like, by the way, this is some, like this is an example of some local optimum, right? But clearly not a global optimum. Here I picked 4 clusters. It has kind of 3 clusters, and it is treated those 2 Gaussian blobs on the right as one cluster, and then split up the ones in the middle here. So, like, how do I evaluate intercluster distance? Like, what is a good metric? Like, of course, I can visualize it, and I can see, like, clearly this is too much, but not all the data is going to be as easily. You always see this as easily in 2D. So what you can do is you can calculate the intercluster distance, so the sum of the distances of each point to its centroids. And what you really want to pick is the K where like after which you don't see a rapid progression of the downwards trend in the intercluster distance. So the right point here, like clearly, like the more centroids you add, the more clusters you add, the smaller the intercluster distance is going to get. But like the delta from 1 to 2 clusters is massive. From 2 to 3 clusters is still pretty big. From 3 to 4 is big. From 4 to 5 is big. But suddenly at 5, it kind of tapers off completely, right? And so whenever you see a knee in this curve for the intercluster distance, this is likely where the right K is for you. So here, this example has correctly identified 5 as the right number of clusters for this data set. So, as I already mentioned, this doesn't find a global optimum, but it finds a local optimum. Like one big benefit of k-means is that it's very fast. So you like often do this. What I just mentioned with running it multiple times and picking the solution with minimum inertia, even running it multiple times with the same number of k, so that like your initialization it doesn't influence your results too much. And like it does well with roughly circular clusters of equal size, but it doesn't do well with any of these kinds of patterns, right? Where you have like these elongated shapes, or even like the half moon example, or anything like with a ring or something like that. Of course, it could do a coordinate transformation and then use k-means, but that would be like a lot of engineering here. And so there's other algorithms that pick up on this kind of stuff easily.
So how come humans are so good at it?
Well, we're good at this in 2D. We're not good at this in 3D or 4D or 5D or 6D, right? So the examples that I'm showing here, like we can pick that out easily, and this is also why visualization is super useful. But in higher dimensions, it's really tricky for us to do. Like one common example for clustering is things like biology, that you look for gene expression patterns, and then you have like thousands of genes and like many samples, and then like as a human, this is just noise. So you need to actually clustering algorithm to make sense of the data in the first place. One way of visualizing higher dimensional data and then trying to manually detect clusters in that is dimensionality reduction, and we'll talk about this right after clustering. And although k-means isn't all that great for unequal cluster sizes. We only have 15 minutes left, so I'm gonna have to go a little bit faster. So dbScan is another clustering algorithm that is kind of like super interesting. It's density-based spatial clustering of applications with noise. This is the name. So density-based, what this means is that clusters are treated as dense groups and no particular shape is prescribed, right? In k-means, we assume that these are just Gaussian or these like roughly circular blobs. dbScan like doesn't prescribe that. So the idea is really that if a point belongs to a cluster, the points that are next to it, that are near to it, should be also points in that cluster. And that's the basic idea. So you have two parameters, like an epsilon. This is the distance that you measure between 2 points. Let's suppose I take this point here, and if this other point is within that distance epsilon, it's considered also part of that cluster. And then you also define a minimum number of points, how many should be in a cluster, because like this, like one could like easily be an outlier here. This is, you see these outliers, but you can of course change them into like your needs. And so there's like a similar visualization. And so if we look at this for these Gaussian blocks, here the circles of course like show the epsilon, so that you get a rough size of rough idea of the size of the epsilon. And so if I run this, what happens is like it evaluates the neighbors for each point. This is what like the circles popping up that you see here. And then if there isn't no points anymore that are similar, it just picks a random point of an unvisited set, and then keeps doing that. And so it like easily identifies these 3 clusters here. And then finally, it treats those here as outliers. And this is kind of like a function of my epsilon, right? If I had a slightly bigger epsilon, then I wouldn't have treated those as outliers. If I now, like, the nice thing is I didn't pick a k, right? I don't have to like say ahead of time how many clusters I want. And then it can also do this kind of like complicated pattern, like this pimply smiley face here. And this is going to run for a while, so I might not wait for it. But you can see that this like progresses, and it will actually correctly identify, like most likely correctly identify, like the eyes, the mouth, and the face on the side. And so like here, like these are points that are likely going to be, or that are definitely going to end up as outliers. Okay. Hierarchical clustering is like a super useful approach in visualization because we get to define our bins flexibly. And there's two types of hierarchical clustering. Agglomerative clustering, where you start with each node as a cluster and then keep merging. The most similar one, and divisive clustering, is where you start with one cluster and then keep splitting it. So I'm gonna demonstrate this on agglomerative clustering here. You've probably seen these kinds of heat maps that are common in biology publications. They have this dendrogram that shows the similarity, but we'll construct this. And so here I'm gonna do a little bit of sketching. Okay, so let's suppose I have these data points that I care about. This is in two-dimensional space. I have A, B, C, D, E, and F. So this is kind of their distance. I have these are two-dimensional vectors, and down here I have a list of them, which I'm going to use to draw this dendrogram. And so the way agglomerative clustering now works is it treats each of those nodes initially as its own cluster, and then it finds the closest cluster. And so if you look at this, the closest cluster here is probably EF. And so we can visualize this by drawing a line here. And then in the dendrogram, we connect those two. And this here is the distance. Okay? Then if we take, if we search for the next, the two clusters that are remaining, now I treat this here, this EF, I treat this as one cluster. But if I keep searching for what are the two closest clusters, I'll probably find AB here. And then I can draw AB like this. And this is, notice the distance between A and B is a little bit higher than the distance between E and F. If I keep doing that, I would add CD. So this is again a little bit higher than my previous distances. And now it gets a little bit more tricky. But what I'm going to do, there's a couple of different ways of linking those up, these clusters up now. And what I'm going to use is the minimum linkage approach. And so in this case, I look at what is the closest point in my clusters, and I'll look at DE here. Those are probably my closest point. And what happens now is that those are connected in the dendrogram like this. And then finally, I connect CD here in the dendrogram like this. Okay, and so now what I can do is if I want to define a discrete set of clusters, I could kind of cut this dendrogram here, and that would result in two clusters, right? In the cluster here and in this cluster. If I were to cut this dendrogram here, I would actually get three clusters. I get this, and this. And so this is super flexible, right? Because I can interactively refine this. This is computationally trivial, and I can manually adjust this. So now, what I used here is this minimum linkage scenario, but I could also do something else, and I'm going to do this a little bit faster now. I could do AB, EF, CD. So I have EF, CD, all of these. Then CD. And now, what would be another metric on how I could evaluate which of those clusters are close? Exactly, I could pick a centroid, right? I could say, hey, this here is my centroid of this cluster, and this is the centroid of this cluster, this is the centroid of this cluster, and it still looks like this here is close, so it will kind of give us a similar similar topology of the tree. And then here, my new centroid is probably somewhere here. And then I would connect this here. So this would give us, in this case, by chance, give us the same topology of this dendrogram, but the distances here are going to be different, right? And that might matter. But it might also be that if I have another example, that I might get a completely different topology of that dendrogram. Another way would be to pick the furthest points, or I could pick the average distance between those points. So these are like what's called linkage criteria. And so here are some, like we talked about all of these actually. Average linkage distance, centroid distance, minimum linkage distance, and maximum linkage distance. These are some of the choices that I have to make when I want to use hierarchical clustering. So here's like an example of, and how here, like we calculated a hierarchical clustering interactively, and then had the slider where you could cut this dendrogram dynamically, and those yellow lines are then discrete clusters that appear based on that. And you've seen this, if you recall, when we talked about tabular data in this hierarchical parallel coordinate. So this here would be this dendrogram at the root, and then this would be a couple of levels down, and this would be a couple of levels down. And so here, each kind of like line plus its, each line represents one cluster centroid, and the shades represent the extent of the cluster. Okay, so we have like 10 minutes left. This is not going to do dimensionality reduction justice, but I'm also not going to talk too much about the math behind it. But there is like a couple of things that are interesting about dimensionality reduction in terms of visualization. So, like, what is the idea of dimensionality reduction? Is to reduce some high-dimensional data set into lower-dimensional space very frequently so that we can plot it. So, like, if you're at all into machine learning, you've probably seen that, like, a lot of people try to visualize their data with, like, fancy new dimensionality reduction algorithms like t-SNE. But of course, there's like simpler algorithms that we've been using for decades, like principal component analysis. And so, what you really like, this is really mostly about plotting. Like, I want to plot this higher dimensional data set in lower dimensional space. And PCA is like a linear mapping by the order of variance. And so, how does PCA work? It tries to kind of like find like the vector or the direction of like maximum variance, and in this blob here, this would be like our first principal component would be like along the trend line of this, because like that vector here, like if you just can retain this one vector, retains most of the information in the data set. Our second principal component would be perpendicular to this here. And so here is like an interactive example to like play with this in 2D. So here we have original data set, and of course, like it's easy to plot a two-dimensional data set in a PCA later. But you can see that it correctly picks up. Like here is like our vector of minimum variance, and if I could keep changing it, you can see how the PCA actually changes it. And like we can of course like do this in lower dimensions. So we could like here this basically if we have something like this, like a mostly linear trend, our first principal component, like if I plot it like this, I'm losing very little information. In a 3D example, like here I have the 3D point cloud with those three clusters. If I like show the principal component, you can see that the first principal component is the axis, like basically through that set of blobs. And our second principal component is like the green line here. And I can reset that, I can play with it dynamically and see how this is oriented. And I can see I'm changing the data set here. And I can see how that changes the principal components. And like this, like in 2D, this is all intuitive. But what happens if we do something like in higher dimensions? Like here's a 17-dimensional example for like 4 countries in the United Kingdom: England, Northern Ireland, Scotland, and Wales. And what kinds of foods and drinks do the people in these countries consume? And so if we look at the like raw data visualization, we see that there is a little bit like English drink a little bit more alcohol than the Northern Irish. And then we can probably see something else. Like here, fresh potatoes are consumed more frequently in Northern Ireland, right? But this is like a visualization. If we all we cared about is to understand how similar or different are those countries, we could do a principal component analysis of this visualization. And if we did that, we can see that Wales, England, and Scotland are kind of similar to each other, but Northern Ireland is kind of the outlier here. So they drink less and eat more potatoes. A different way of doing dimensionality reduction is multidimensional scaling. And when I say multiple dimensional scaling, I really mean that this is like a family of techniques. It's based on projecting a similarity matrix. Like you have to, of course, think about how you compute similarity and how do you project the points. I'm not going to go into this because this is like its own lecture, but this is like a method that has been very popular for text analysis, and this is also what we used in this in our design critique, what was used in our design critique from last week or from Tuesday. One thing to note about all of these dimensionality reduction methods is like what you really can interpret is points in their local proximity and like in these neighborhoods, but you shouldn't usually interpret absolute space. And you also need to be aware that there might be artifacts here. So this is like a principal component analysis of dissertations at Stanford. And what you see here is petroleum engineering seems to be roughly as close to medicine and neurobiology and biology than it is to, let's say, computer science or like material science and engineering and statistics. So kind of like, it's an odd thing, right? Because you would expect that petroleum engineering is probably somewhere up there with mechanical engineering and geology and so on. And so this is likely an artifact of the dimensionality reduction. And if you look at this chart here, you can actually see what you can do and what you also need to do if you use a dimensionality reduction approach is that like you need to communicate this error that you have with the projection if on demand. So for example, here you see like now a plot that is focused on petroleum engineering, and you show the absolute correct distances to each of these other disciplines. Of course, now you can't judge the relative distances between these other disciplines anymore, but this is like a perfect representation of the similarity of petroleum engineering to these other fields. And you see that in this plot that petroleum engineering is actually close to physics and to the other engineering disciplines. So that does make them a lot of sense. So there's like a live demo here, which I'm gonna skip over. Yeah, the rest of these slides, and like we have a lot of stuff and only one more lecture to do, so I'll just jump over them and you can look at them at your pleasure. This is like a technique that kind of shows, like explores like these errors in projections. So there's a nice video that I would recommend. But some like more fancy algorithms are like t-SNE and UMAP, and these are like modern nonlinear algorithms that use different transformations for different regions, and so therefore are like pretty good at detecting these like similar features. And I'm linking in the slides to like an article here, like how to actually interpret t-SNE, and then here's one about understanding UMAP, and so like you can like build some intuition by like here I've actually like picked like a regular grid as input data set, and this is what t-SNE produces out of it, right? Here I have these two blobs, and this is what t-SNE produces out of it, like as it keeps iterating, and then here's like a couple, like three dots, and you see that it actually works pretty well. Even if I have some like structure like this shape here, it will kind of preserve some of that structure. And of course, like this is like two-dimensional examples, but this article is pretty good at like explaining what are the problems with interpreting t-SNE plots, and there is a similar one for UMAP. UMAP is like basically fundamentally these are all graph-based algorithms, and UMAP does similar things to t-SNE, but is a lot faster. And then like last thing for today is like you can use those approaches to do some pretty cool things. Like here, this is like projecting Wikipedia articles as they're being edited into space, and the curve here shows like the sequence of edits. And so here you have the Wikipedia article for chocolate, and you can see that we essentially, like this article was edited, and then there was some minor edits, and then kept working, and then there were a couple of smaller edits. Then there was a little bit of oscillation, and then there was people kept editing it. But then if you have like a controversial article, like politically controversial article, like the one about Palestine, for example, you see these like oscillations between states because people are likely doing edit wars here, right? So they delete sections, restore sections, delete sections, restore sections, and so you get this oscillations between states. Okay, that was it about aggregation for today. On Tuesday we'll do like a summary of text and set visualization, and then Thanksgiving on Thursday.
Does it include the top pages or just the main pages on Wikipedia?
This is like the article from chocolate and the article for Palestine.
Because it could also be people just moving sections out to.
Yeah, but then you wouldn't see these like these back and forth patterns as you do here.
You can only edit more than three revisions, and then it gets locked.
Yeah,
And then you go to top pages, and then you're supposed to.
Yes, I think this data might have been a little bit more.
Yeah, again, I don't really need
Yep. Sure. Yeah. Well, like in practice, you probably have to do it. So what I would suggest is if you need more time for the exam is that you will simply like do the first part of the exam here, and then come with me to my office and do it like once a week. I'm fine with like letter. I can do it this only. I can do it this only is fine.
Yeah, I'm gonna try. Well, I'm gonna try. Okay.
I can do it if you want to, but I
Okay. So, yeah, just let me, and I can, yeah, I'm just like experimenting, because we didn't really agree on it, that's like, I wasn't sure, because like, my kid and other people had like different examples, like ways of doing it, so some people get out of using it.
Yeah, I think after the is tricky, right? Like, it makes sense for me to like
And that's one of the things
I mean, look at like what are we talking about in terms of like how is it done in the homeworks and stuff.
Yeah, so that's the problem now, it's just the problem with bar chart is that I don't really, everything is continuous for that scale, but I was thinking if you have discrete values, like in our case 1, 2, 3, 4, 5, then that would be better for like fitting like experiment.
Yeah, I would almost go, I'll take a look at it too because I'm interested in finding out what